Hi everyone, we're going to work a little bit on L'Hopital's rule now. I'm actually looking at this scene that I'm calling it 2.8, but I think currently it's numbered 3.5, but definitely it's about L'Hopital's rule. So I want to start off here. This lesson is sort of built around being in person and getting to ask you questions, but if you'll cooperate, I can still ask you questions and hopefully help you spot something that's really interesting here. So I have two questions in the beginning, and I want you to look through these and see if you can pick what you think the answer is. If you aren't sure, that's fine. Make a guess. You don't have to tell me. This is only for yourself. I am going to talk you a little bit through what exactly I'm asking just to make sure you're seeing it. So I have two functions, f of t and g of t, and I'm building a fraction, f of t divided by g of t. And I know that when t gets really close to some specific x value c, the y values of f go to 0 and the y values of g go to 0. So the question is, what happens to this fraction? So basically it's hitting the top is headed to 0 and the bottom is headed to 0. So what happens to the whole thing? So again, please pause, look at it for a second if you need to. Make a guess. I know you're going to sit there and try to not make a guess, but I really want you to make a guess. Okay, so second question is, what if we're doing the same thing, but instead of the top and bottom going to 0, they're going to infinity? So the first one was of the form 0 over 0. The second one is of the form infinity over infinity. So same idea here. You've got the same options. Do you think that the limit will approach, the fraction will approach 0? Do you think the value of the fraction will approach 1? Do you think the fraction does not exist? The value of the fraction doesn't exist? I'm saying this strangely. The value of the limit doesn't exist. Do you think it's approaching -5 or do you think it's approaching infinity? Okay, so please make sure you have a guess for both of those. And then we're going to work through some examples. And this is actually really good because not only does it help us figure out if we've got the right idea for these first two questions, it also gives us some review from way back in the very beginning. I think it's 1.2 where we were finding limits algebraically. So I love this section at the end. We get to practice derivatives, practice the old way of finding limits, and learn a new really nice slick way of finding limits. Okay, so before I give you an answer to the last question, I want to work through some examples and see what's happening. So the first one, I have a fraction, t plus 2 to the 7th over t plus 2 squared. And I'm supposed to find the limit as t approaches -2. So always when you're finding limits, the first thing you should try and do is just plug the number in. If your function is continuous at whatever that t value is, it's a really easy question. You just plug in the number and get the answer. So here, if we let t get really, really close to -2, the top is going to get really, really close to 0. In those parentheses will be something really close to 0. When we raise it to the 7th, it's going to get even closer to 0. So when we raise tiny numbers to big powers, they get little. And the same thing with the bottom, that's going to approach 0. So this is one that we can tackle using our old methods. So we're going to go ahead and say, well, algebraically, and this is a really interesting question when you have a 0 over 0. Algebraically, I can do a little canceling. So I get to cancel out a t plus 2 squared, which means there's none left in the bottom, but there's a t plus 2 to the 5th left in the top. And now if I go and try and plug in 0, I don't have the 0 in the bottom, which means I no longer get that domain error. I now get something totally valid. When t approaches -2, I'm getting basically 0 to the 5th power, which is going to be 0. And you want to keep remembering that we're talking about limits. So yes, we do plug in the number when we can, but the question is still about what's happening really close. If t is really close to -2, our answer is really close to 0. So it's not actually saying when t is -2, our answer is 0. Okay, so we started with a 0 over 0 limit, and we got 0. So back here to question 1, what happens to your 0 over 0 limit? If you said it goes to 0, you are correct. Okay, let's look at another one. Sine t over tangent t as t goes to 2 pi. Okay, so if we're thinking unit circle, which I like to do for these, we've gone all the way around. We're back over at our starting place. Sine is our y value, which is 0. So this is approaching 0 as we finish our full lap around the circle. Tangent is the slope. So as we move back around, we end up with a horizontal line. So slope is also going to 0. So this is another 0 over 0. Whenever we get one of those, we want to see if we can use algebra to fix it. You can't always, but sometimes you can, and it's a really nice way to do these. Okay, so the algebra here is just to recognize, if I could quit erasing everything I wrote, that tangent is the same as sine over cosine. And then we're dividing by a fraction, so we can multiply by the reciprocal. So I have a sine t, and then I have a cosine t over sine t. And I get to cancel that sine t. So I'm really just left with the limit as t approaches 2 pi of cosine t. So when t is really close to 2 pi on my unit circle, remember cosine's your x value. So my x value is really close to 1, which means that this thing is approaching 1. So if t is really close to 2 pi, the limit is going to be 1. The y's are going to approach 1. Notice that we started with a 0, 0, 0 over 0, and we ended up with the value of the limit being 1. So back to question 1. If you said that you thought the value of the limit was going to be 1, you are correct. Okay. C. Similar to the first one, so now t is approaching 1, which means the top is going to get really close to 0. 1 minus 1 is 0. And the bottom is also going to get really close to 0. This is another one where we can just go ahead right away and cancel. So we get limit as t approaches 1 of 1 over t minus 1. So unfortunately, we didn't get rid of that problem 0 in the denominator. Right now, if I plug in 1, I get 1 over 0, which is a bad sign. Generally, if you don't have that 0 over 0, you have something else over 0, you're going to have some kind of asymptotic behavior. So the question here is, do both sides go to, so vertical asymptote is what we're thinking. Do our y values go to positive infinity on both sides, negative infinity on both sides, or do they head different directions? And you can figure that out either by thinking, what happens if I plug in something a little bigger than 1 versus a little smaller than 1? Or if you're good with your transformation still, if we think of a 1 over t graph, since we're subtracting 1 from the t, this would shift right 1. So our usual shape like this. So again, if that doesn't work for you, you can plug in like 0.5 and 1.5, for example. You could get even closer than that if you've got a calculator handy. Actually, you might not need it here. Somehow you need to figure out that this is headed to positive infinity on one side of t equals 1 and negative infinity on the other, which would tell you that this does not exist. If both headed to positive infinity, then we would say the limit is infinite. Negative infinity, the limit is negative infinity. But if they had different directions, it does not exist. So 0 over 0 limit, and we got it does not exist. If you thought the answer to question number 1 was C, you were correct. Okay, am I getting predictable yet? Probably. To continue with this a little bit. Ooh, I don't know what I made here. I thought I was going to be predictable and have one that equals -5, but it looks like I decided to mix it up. So here, it's still a 0 over 0. But now, when we cancel, I get a 1 over t minus 1 squared. And I'm sure I wanted to show you this just to make sure you realize that asymptotic behavior doesn't always mean you have to say does not exist. Here, instead of taking a 1 over t graph, we took a 1 over t squared graph. And for that one, both branches head up to positive infinity. So this time the answer is actually infinity. So if you thought the answer to number 1 was E, you are correct. Okay, last one on this. As t approaches 0 in part E, we get another of those 0 over 0 limits. I can use a little algebra here because I can factor a t out of the top. T minus 5, t. And then we can cancel that t out, and now I can actually plug in 0. And when I'm all done, I get a negative 5. Oh, I'm so tricky. I mixed up the order, but there it is. If you thought the answer was D, you are correct. Okay, so here is the important thing for you to get from this. Well, a couple things. One, that review on finding limits algebraically. Those ones weren't terribly messy, but just as a reminder, if you get a 0 over 0 limit, you should try to use algebra. Try to factor and cancel. Okay, the second thing I'm really hoping you're getting from this is that 0 over 0 limits are interesting because anything can happen. They're not always going to be 0 or 1 or undefined or infinite or something else. They can be anything, and that's what makes them really cool and fun to work with. So use algebra if you can. Don't have fixed in your head that you're going to get a certain type of answer from a 0 over 0. Okay, so for number 2, maybe you can predict that this will give us some of the answers for number 2. But still, I think really good review here of finding limits. So this first one is a really nice horizontal asymptote review. We want to know if t gets really, really big, what happens to this fraction? And there's kind of a two-step process to figuring that out. The first step is if the power, the biggest power, let's use our math words here, the degree of the top and the bottom are different, then that's going to trump anything that's going on with adding, subtracting, multiplying by constants. And that is true here. The bottom is third degree and the top is second degree. So regardless of that 2 out in front of the t squared or anything else that's happening, if I plug in a big number, say I plug in 1,000,000 or 1,000,000,000, I'm going to have 1,000,000 squared on the top. And yes, that's multiplied by 2, but that's not anywhere close to taking the million and cubing it. So when I look at this fraction, right now we just kind of have to reason our way through it. I actually think that's a very important skill, but we will work on a way that does this a little more algebraically. That's what we're headed towards now. But right now what we see is the bottom is significantly larger than the top when we plug in big numbers, which means this thing's going to approach 0. The bottom of a fraction is way bigger than the top. It approaches 0. Hope I don't make you ill with my scrolling, which means if you thought the answer to number 2 was A, you are correct. For B, we actually can use some algebra on this one as t approaches 0, and I'm specifically looking at from the right, so I'm probably trying to avoid some different things happen on different sides. But what I see here is as t approaches 0, oh, and I didn't say this up above, but this was an infinity over infinity. If you plug in big numbers, the top gets big and the bottom gets big. But the bottom gets big faster, which means it approaches 0. Okay, so for this one, we're plugging in tiny positive numbers, which is going to make this get really, really big. Adding 1, it'll still be a really, really big positive number. And then the same thing in the bottom. What in the world was I getting at here? We don't really have to do algebra because now that I'm looking at it, it's 1 over t plus 1 divided by 1 over t plus 1, which of course is going to equal 1. So we're really just looking at the limit as t approaches 0 from the right of 1, which is 1. But it still gets my point across. That was actually an infinity over infinity, but if you reduce it down using algebra, you can get 1. So infinity over infinity limits can equal 1. Okay, a couple more. I don't think I did all the examples, all the different numbers, but I think we'll get the point. Here's another one. If you plug in really big values, the top's getting really big, the bottom's getting really big. But once again, they're doing it at different speeds. On the bottom, we have a big number. On the top, we have that big number squared. So the top is growing a lot more quickly than the bottom. When the top of a fraction gets a lot bigger than the bottom, the whole thing gets big. So we can have infinity over infinity limits go to infinity. And I have one more. We'll see who I'm leaving out off the list. Last one. Okay, so again, when I plug in big numbers, this is infinity, The bottom is actually going to negative infinity. So I'm looking at 5 times a big number to the 4th on the top and a big number to the 4th, but it's minus that on the bottom. But still, same idea. I don't really care if it's positive or negative infinities in here, same idea. This time it gets interesting because they're both t to the 4th, so they're actually both growing at somewhat of the same rate. And this is where it becomes a question of, okay, so we're basically going to have like a million to the 4th on the top and the bottom, and that'll balance out. Now I care if it's 5 times a million to the 4th, or 2 times a million to the 4th, or negative 1 times a million to the 4th. So here, the million to the 4th will balance itself out, but on the top, we have a factor of 5 attached to that, and on the bottom we have a factor of negative 1 attached to that. So this is going to go to negative 5. If you feel at all unconvinced about that, go just snag some technology calculator or whatever and plug in some big numbers and just look at what's happening. I'd love for you to be convinced. This making sense will be really helpful. Okay, so that was a negative 5. It looks like I neglected the does not exist, but I will just say that my point is the same here. Using some algebra or basic knowledge of rational functions, you can figure out the answer to some of your infinity over infinities. And what you should see right off the bat is there is no rule about what that's going to be. It could be 0, 1, infinity, undefined, any other real number out there. So all wide open. So this is what this section is going to be all about, is what's a nice way to find the value of the 0 over 0 or infinity over infinity type limits. Okay, long intro video. We'll jump into examples next.